Students, in this session, let us discuss a few concepts related to mass spectroscopy. So, for mass spectroscopy, you have only the principle of the mass spectroscopy, then instrumentation, then some definition of parent peak as well as the base peak, and then MAC laboratory rearrangement with respect to butyraldehyde. This is what you have. So, what is this mass spectroscopy? The basic principles of mass spectroscopy. But for let us see what is this mass spectroscopy. Mass spectroscopy is an analytical technique that ionizes chemical species and they sorts the ions based on their mass to charge ratio. So it is an analytical technique that is used to determine the mass of an organic compound. What it does, it ionizes a chemical species, ionizes it, breaks it down, and then sorts this ion based on their mass to charge ratio. In simple terms, a mass spectroscopy measures the masses within the sample. Within the sample, so it measures the mass of the fragments that are. This is the basic principle of this mass spectroscopy. Mass spectroscopy is the most accurate method for determining the molecular mass of the compound and its elemental composition. In this technique, the organic compound in its vapor state is bombarded with a beam of high energetic electrons. Okay, what is that is? A molecule. Let this be a molecule. What is done is this is bombarded with high energy electron. What is done is this results in the removal of another electron, resulting in the formation of a radical cation is what is formed. See, this is the neutral molecule. It is bombarded with an electron. This removes an electron. It results in the formation of a radical cation. Okay. Then fragmentation may take place into smaller units. That is cation and a free radical. Okay, radical and a cation is generally formed. Okay, so what happens is in this technique, an organic compound in its vapor state is bombarded with high energy electron beam, bombarded with a beam of high energy electron, that is having the energy of the order 6700 kilojoules per mole in vacuum. The molecules of the organic compound gets ionized. It gets ionized and they split into fragments. So these fragments are later ionized. Detected, and they are sorted based on their charge to mass ratio, sorry, mass by charge ratio, and they are identified. So the mass spectrometry technique is a most important technique which measures the masses of these. It measures the masses within the sample. Okay. The instrumentation part. The instrument consists of three major components. One is the sample introduction. That is the inlet. Then comes the vacuum pumps. Okay. There will be a source, there will be an analyzer, and there will be an ion detector. Okay, gas phase ions, then ion sorting, and the ion detection. So sample introduction is done here. Okay, then the analyzer where the ion sorting takes place, and then ion detection, and next it goes to the data system. Okay, we have the source, then we have analyzer, then we have the ion detector, then it goes to the data system where the data output you get in the form of some lines like this. Yeah, that is the mass spectrum is what you get. Okay, now the first step is this is ionization. There are three major steps that are involved. One is ionization, then next one is acceleration, third one is deflection, and then the fourth one is the analyzer. First, what is done is ionization is done. First, ionization of organic compound is done. The first and the most important step in obtaining the mass spectrum is to ionize the sample. So this is called as a mass spectrum. The lines that you get is called as the mass spectrum. It is based on their mass by charge ratio is what you get. Okay, m by z ratio is what you get at. Okay, mass to charge ratio. Now, the most important method in obtaining the mass spectrum is to ionize the sample under examination. Think that this is the sample under examination. It has to be ionized first. It has to be ionized first. So the minimum energy required to ionize an atom or a molecule is called as its ionization potential. Okay, if you want to remove an electron, the energy required is called as an ionization potential. The common technique used for the production of ions is by bombardment of the electrons. So they are bombarded with the electrons and ionization takes place, resulting in the formation of an ion. So this is the first step that is done. Okay, first step that is done. Now after that, the second step that we do is acceleration. Acceleration. What actually happens in this acceleration? Acceleration is a simple step where the ions are placed between the set of charged parallel plates. Okay, they are placed between the set of charged parallel plates. They are placed between the set of charged parallel plates like this. Okay, so this will be an ionization chamber, or the ion beam moves like this. Okay, they are placed in between the set of charged parallel plates. The ions will be repelled by one plate and the attracted by the other plate. Okay, getting this? So once they form ion, then they pass to the, then they are accelerated. Accelerated. That means acceleration is a step where the ions, what they are placed in between the charged plates. So one plate will be attracting it, other will be repelling it. The ions will be repelled by one plate and attracted by other plate. There is a slit cut in the plate which the ions are attracted to. This force of attraction and repulsion forces the ion through the slit at an accelerated rate. So they get attracted by one plate and they repelled by another plate. This force of attraction and repulsion forces the ion through the slit at an accelerated rate. Okay, so this speed of an acceleration can be adjusted by changing the charge on the plate. So this is one thing. First ionization is done, then these ions are accelerated. The third step is deflection. Now, ions are deflected by a magnetic field surrounding the instrument. So there will be a magnetic field surrounding the instrument. So these ions, whatever they are accelerated, they are deflected by the magnetic field. The amount of deflection depends upon the mass and the charge of the ions. If the ions are heavy, with a positive charge of 2 or more, they are deflected least. Okay, so we have different ion stream C, ion stream A and ion stream B. For example, if this is a magnet, think that these are the magnets. Now ion stream B, see, this is ion stream B. Okay, ion stream C, ion stream B, as well as the ion stream A. See, what is this ion stream C? The heavier ions and the ions with +2 charge or more are deflected least. Okay, they are deflected least, right? So they come out like this. Ion stream C, ion stream D. The lightest ions and the ions with one positive charge are deflected the most. They are deflected the most. Here only they get deflected here only. They are deflected the least. The ions at the correct mass by charge ratio, they travel to the detector. This is ion stream B. Okay, so if the ions are heavy and the ions with +2 charge, they are deflected the least. The lightest ions, they are deflected the most. Okay, the ions at the correct mass by charge ratio, they travel through the detector. Okay, the mass to charge ratio is determined from the ion that hits the detector. So this ion hits the detector and the mass to charge ratio is determined. For resolving the ions into their characteristic mass components according to their mass to charge ratio, so we use an analyzer. For detecting the ions and recording the relative abundance of each of the resolved ionic species. Okay, so now what happens here is the fourth step is analyzer. First ionization takes place, then acceleration takes place, then deflection takes place. Okay, some are deflected the most, some are deflected the least, and then some come out without undergoing a deflection. So this ion stream B, okay, so there will be an analyzer here, there will be an analyzer. Okay, when the ion stream B reaches the detector and hits the wire, there will be a wire here. Okay, when it hits the wire, the ion stream B passes through this and it reaches the detector. When it reaches the detector and it hits the wire, on hitting the wire, they become neutralized by an electron jump. They take up an electron and they become neutralized. The amplifier, what it does, it picks up the current being created between the wire and the ion and amplifies the signal being detected. Okay, what are the ion stream B that comes out? Okay, it hits the wire, okay, of the detector system. On hitting the wire, it becomes neutralized because it picks up an electron from them. So the amplifier picks up this current being created between the wire and the ion and amplifies the signal. Hence, you get a mass spectrum is what you get, where you get lines based on their charge to mass ratio. So let us see how the mass spectrum will be there. Okay, so we have, this is how a mass spectrum will be there. So we have relative abundance. Okay, this is m by z ratio, based on the m by z ratio. So you get lines like this. You get lines like this is what you get. Okay, corresponding to the charge by mass ratio is what you get. Okay, so we come across two types of peaks here. One is molecular ion peak, other one is the base peak is what you call it as. Now, what is this molecular ion peak or a parent peak? Parent peak or a molecular ion peak is a peak that depicts the ion of the molecule without fragmentation. That is, it is a peak that has an highest m by e ratio. Okay, it has an highest m by e ratio. So that corresponds to the molecular mass of the compound. If there are isotopes, you get some +1 or +2 values what you get. See, so this is the molecular ion peak here, or a parent peak. Parent peak that corresponds to the value of this mass corresponds to the mass of that compound that was under examination. If there are isotopes, you get this. For example, if there is a chlorine atom present, you know that chlorine exhibits two isotopes. One is chlorine 35, other one is chlorine 37. If a molecule contains chlorine atom, we get a small peak at +2. Think that m is the mass of a compound, then you get some peaks at m+2 value also. Why? Because of this isotope. So parent peak is a peak whose value corresponds to the that is molecular mass of the compound, that is the ion of the molecule without fragmentation. Okay, without fragmentation, whatever the molecule that you get, that value is what it depicts. Then comes the base peak. Base peak is the most intense peak or the tallest peak in the mass spectrum. Okay, it is the most intense peak. It is the most intense peak or the tallest peak in the mass spectrum due to the ion with the greatest relative abundance. Okay, so now parent peak and the mass peak. Parent peak is nothing but it is a peak that depicts the ion of the molecule without fragmentation. Without fragmentation, the molecule that you get, once the ions is formed, that value it predicts. If there is an isotope, you get another smaller peaks at that m by 2 or m by 1 value based on the isotope. So then comes the base peak. Base peak is the most intense peak. Okay, now we need to discuss the last part of this mass spectrum that is there for syllabus is the rearrangement. Rearrangement is what we are going to discuss now. The rearrangement is referred as Mac Lafferty rearrangement. What is this Mac Lafferty rearrangement? Now, let us see the Mac Lafferty rearrangement is a characteristic fragmentation of a molecular ion of a carbonyl compound containing at least one gamma hydrogen. If a carbonyl compound contains at least one gamma hydrogen, so it undergoes characteristic fragmentation, which we call it as Mac Lafferty rearrangement. For example, so we have a carbonyl compound. We have a carbonyl compound alpha, beta. This is gamma carbon and this is a gamma hydrogen. So we have a carbonyl compound containing a gamma hydrogen. If carbonyl compound contains a gamma hydrogen, they undergo characteristic fragmentation, which you call it as Mac Lafferty rearrangement is what you call it as. So what generally happens you see here? When you bombard with that, electron beam, what happens here? Okay, now this electron, we have, when there is a bond, there will be two electrons. One electron moves here. This hydrogen will be taken up by this oxygen. Okay, so Mac Lafferty rearrangement, it involves the migration of gamma hydrogen, followed by the cleavage of beta bond, This hydrogen moves here. So we have a plus charge here because of that ionization. So what happens is this moves here. So see, when you bombard it with an electron, you get an ion radical is what you get, right? So what happens is this gamma hydrogen moves here. Okay, so this, there will be a, when I say a bond, there will be two electrons. One electron moves here, the electron of this, they form a bond. Then one electron moves here and this electron moves here and this electron moves here. So resulting in the formation of here. Electron moved here and electron moved here, so there will be a formation of a double bond here. So this bond breaks now. Why? Because one electron moved here, one electron moved here. Okay, one electron moved here and one electron moved here, so this bond also breaks. So you get a double bond here. So what will be remaining is here. That is oxygen to oxygen, hydrogen is linked. Double bond as usual. You get this. This is what you get. So this rearrangement is referred as Mac Lafferty rearrangement. I'll repeat it once again. So this is shown by carbonyl compound containing at least one gamma hydrogen. This is alpha, beta, gamma. This is gamma hydrogen. So it involves the shift of gamma hydrogen. So this hydrogen shifts here. See, whenever you bombard it, you get a radical ion is formed. Oxygen contains two pairs of electron. You get a radical ion. So it has only one electron. So this, it takes up one electron and comes here. This electron, so they form a bond. So one electron is remaining here. This moves here. So this bond breaks. So this electron, here there are two electrons. One electron moves here. So remaining electron goes to this gamma. So what happens is here, this bond breaks. So you get a double bond like this. And what is remaining? O, H, and a free radical is forming. So this arrangement is called as Mac Lafferty rearrangement is what we call it as. Now, so for a syllabus we have Mac Lafferty rearrangement with respect to butyraldehyde as an example. So let us see butyraldehyde as an example. Butyraldehyde or butanol. So this is very, very important. So you should concentrate on this. Butanol or butyraldehyde. So let us draw the structure of butyraldehyde. Butyraldehyde contains 4 carbons. So it will be C, double bond O, C, C, C. 1, 2, 3, 4. This is H, 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 H. So this is alpha, beta, gamma. Now, When you bombard it, what do you get? You get ion radical is what you get. Now what happens is here. Now this hydrogen moves here. Okay, this hydrogen moves here. If I getting this, so this hydrogen moves here. This electron, right? So they form a bond, right? Like this. This moves here. This electron moves here. This moves here. So see what happened here. A bond is formed between O and H. Electron moved here. This electron moved here. So this bond breaks. So what you get? You get 2 carbon remaining. This bond breaks. This bond also breaks. You get 2 carbon. C double bond C, H, 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 H. So this is gamma, and this is the beta carbon. These 2 carbon. This bond has broken now. Okay. So what is remaining is here C. This electron moved here. Double bond C, H, H. This is alpha carbon. H that is remaining. Now this OH. So this is carbonyl carbon and this is the alpha carbon. So these are the 2 fragments that you get. 2 fragments that you get. This is what you get. You get 2 fragments like this. Okay. So this is equivalent to ethylene. C double bond C, H, H, H. Okay. And another enol form of this. C double bond C, H, H, OH, H. So M by Z of this is 44. 44. So M by Z of this is 72. 72. Okay, this is called as the Mac-Lafferty rearrangement. Lafferty rearrangement, where gamma hydrogen shifts here, the electron move here, so it forms a double bond. This bond breaks. So this is what is formed. Now, when you look at the mass spectrum of this, the mass spectrum of this will be like this. You have this relative intensity here, and M by Z ratio is what you have. So you get a peak at 72. M by Z 72 is what you get. That is called as a parent peak. Okay, molecular ion peak. Then you get a base peak at 44. At 44 is what you get. This is due to the Mac-Lafferty rearrangement. So due to the Mac-Lafferty rearrangement, what is formed? Because of this Mac-Lafferty rearrangement, this molecule is formed. This molecule is formed which has M by Z value as 44. So we are going to get a peak at 44. So this is about the mass spectroscopy. Thank you.